All right, so it's great talking with Sylvie Boldo, and I'm talking about formalization of Lebesgue integration.
Thank you. Can you hear me? Great, thanks. My name is Sylvie Boldo. I'm a computer scientist, even if it seems to be outdated. We're both computer scientists and mathematicians, and I'm interested mostly in verification of programs. And by that, I mean usually numerical programs. And then I came to get interested in applied mathematics programs. And to prove them, you need many things, and you need the maths, and you need the programs. And so I came step by step to the formalization of mathematics. And what I will show you is really formalization of one piece of mathematics, which is Lebesgue integration. A few disclaimers. So this is joint work with a bunch of people. François Clément and Vincent Martin are people from applied mathematics. And Florian Fessel and Michaela Meiro are more from computer science part. So it's really a mixed team. And we really needed that for this piece of work. This is done in Coq and not in Lean. And it's okay, I can keep on. And third disclaimer, there is nearly no computer arithmetic, because people might know that I'm more a computer arithmetic person than a mathematics person. But so there is nearly no computer arithmetic, you'll see at the end. And so I will begin with an introduction, saying why I need that. So mathematics, all of you know about mathematics. It's wonderful. You have real numbers, integrals, derivatives, and theorems that are true, of course, because they are in the literature. And you have applied mathematics, and then you're going to numerical schemes, convergence, and so you have something which is slightly going towards computer science, like algorithms. And of course, theorems saying that algorithms are correct. And then you have real life, and real life holds on a computer. And on a computer, you don't have real numbers. Well, usually people don't use real numbers on computers, they use floating point numbers. And so you have round-off errors, overflows, underflows. I can talk about that for hours. And you have implementations, so you might have implementations errors, because programmers are just human beings. And so you have programs, and you don't have anything looking like theorems. You have programs, and hopefully you have tests, and you hope that it's correct. And if you want to add something like paranoia, meaning you want to be very, very sure that your program is working, then you need to go all the way down from the mathematics to the program to be sure that your program at the end will indeed give you the expected answer, whatever this means. And so motivation is solving differential equations. They might be ODEs or PDEs. I'm more interested in PDEs, but that doesn't change a lot. They are very useful for weather forecast. You can forecast that tomorrow it will be cold here, but usually you're more interested in more details than that. Nuclear simulation, optimal control, and so on and so forth. And usually you cannot solve them. You cannot have exact equations solving your differential equations, so you need approximations. So schemes, algorithms, and things like that approximate your differential equation on small things. Discrete grids, discrete volumes, so things like that. And you have mathematical proof that tells you something like convergence. If your grid or your volumes is very, very small, then you're getting the exact solution of your differential equations. So something usually called convergence. And then you have real programs implementing this scheme or this method, and that's the thing that you would want to prove that it's correct. And so that's the reason we want to machine check this kind of program. And there was a talk this morning saying we need big goals. And I have big goals. I want to go towards the finite element method. That's my own big goal. Why? Because it's used in practice and because there have been bugs. So we all love bugs because it justifies our formal proofs. And this is an offshore platform. And it just synced, meaning that it was on water and then it was underwater. So that's not the expected behavior of the offshore platform. And so this was due to a bug in the finite element method. I cannot say much more than that because I'm not an expert, but it just failed, you know. So that's good. That means that it's really useful and it really needs to be granted. And so we have complex geometries. So usually what I like is finite grids, meaning very simple things like that. Doesn't work, doesn't matter. So I like grids, but in real life it's not grids, it's more things like that, meaning a bunch of triangles or tetrahedra called a mesh. And we will solve our differential equation on this mesh. And one solution, which is very useful, is the finite element methods. It encompasses many methods for connecting these simple elements between them, because you will solve your differential equation on your volume, and then you need all your volumes to talk to one another to get the solution on all of it. And so I would like to get some certainty on this thing. And so we need to have some proofs of the mathematics of the finite element methods, and later on some proofs on the library, which is really implementing. So we had one in mind, which is called Felice, which is used in biomedical, but maybe when we have finished the mathematical proofs, we'll switch to another one, because it takes time. And so we want to check this program. But first thing, let us try to at least understand and then formally prove the mathematics. Because my experience is that you need to understand the mathematics and get the mathematical properties in order to prove the program. And so the first step was to prove the Lax-Milgram theorem, which is well known in the finite element methods. And we had very nice mathematicians who wrote to us a very detailed pen and paper proof, which was 50 pages long. So it's a big thing. And it was very detailed enough so that we could make the formal proofs on that. And it was something like 700 lines of LaTeX and 200 characters. And we had dependencies, which was very fun because we could make a graph. Okay, it does not fit on the slide, I'm sorry. And this is a dependency graph of the theorems. So it's much bigger than that. But it's kind of fun to see how the dependency goes. So we promised to make some kind of analogous graph of the Coq proofs, but we did not make it yet to compare. But it's very difficult to browse in this kind of graph. It's too big. And so we decided to prove this thing, and we built upon a library, a Coq library called Coq-Lico, which was developed by Guillaume Melchion, Catherine Lelay, and myself, which has general spaces, meaning more than just real numbers. I will explain that in the next slide. And he had many existing theorems, but it was not exactly the space that we needed, so we needed to enrich it. And this is the basic hierarchy of spaces. So abelian groups can do that like that. So this is an abelian group like you expect, like was shown this morning, nothing special. And then we have rings and model space, which are vector space, but of maybe infinite dimension. And an abstring, meaning a ring with an absolute value. And a norm module, meaning a model space with a norm, with all the properties of a norm. And we also have a topology based on filters à la Bourbaki. So filters, well, let's say neighborhoods. If you don't know filters, it doesn't really matter. And so we have balls and we have neighborhoods. And with that, we can have a limit, meaning complete space, meaning, which is a space which has indeed a limit inside it. So we have Cauchy sequences and filters and so on. And if we add all of this, if you have both norm modules and complete space, we have a complete norm module, which is not very surprising. And we have a bunch of theorems on that. And then for the Lax-Milgram theorem, we added two things. We added pre-Hilbert spaces, which is in blue here. So pre-Hilbert spaces are just model space with an inner product. So an inner product like you expect. And from that, we can define a norm. And the norm has, of course, all the good properties so that we can get a norm model. And if we add the limit, then we get what's called a Hilbert space, which will be the basic of the next theorems, and which is both complete and as an inner space. And so with all those things, and many others, we were able to prove the Lax-Milgram theorem. So we had results about functional space, linear and Wheeler mappings, a fixed point theorem. in a subset, which was different from the previous ones. And we can decide if a space is 0 or not, which is kind of funny. And we have the normal functions, an operator norm. And we have 8 equivalence definitions for the continuity of linear mappings. So because we needed all of them, so we proved all of them. And we have definition of pre-Hilbert and Hilbert spaces. And so we can define what's very useful, which is continuous linear mappings. So we can expect it's linear mappings that are also continuous, and it's CLM. And we were able to prove they form a norm module so that we can consider the continuous linear mapping over the continuous linear mapping over something. So that we can, and we really used this thing inside the proof. And then we prove Milgram theorem and Sylvie lemmas that I will show just in the next slide. And for a total about 10,000 lines of code, just to give you an idea. And so what we prove, there are those things. If you don't understand all of it, that's not really important. I will just give you the main points. The main points of Milgram theorem, it's a representation theorem, meaning it gives you an element that can represent something else. And it's this U here that can represent the function, yes, the function f from the bilinear mapping. And that gives you an element which represents your bilinear map. And then Sylvie lemma is a theorem that gives you a distance, meaning that what will happen is that you apply Milgram theorem on your whole partial differential equation, and that will give you a U, and you apply it on the mesh that will be the mesh of your finite element method, and you get this U8, U phi, in English, phi, sorry. And you get the difference, and so this lemma allows you to state the difference between the solution using the finite element method and the perfect mathematical solution. So it's why it's used. It's help you to get you the convergence of the finite element method. And so we proved all of those. And so this was really the first step towards finite element method. So we got Milgram theorem, and we require the subspace to be complete, but that was done by my PhD student for finite dimensional subspaces, and the mesh are like that. And we require E to be a Hilbert space. So as defined before, with an inner product and so on. And E will be, in practice, instantiated by a subless space called L2. And for L2, we need to prove that it is indeed a Hilbert space. And for that, we begin to say, well, we will axiomatize Lebesgue integration and prove that it's a Hilbert space. And then we discovered we were not very sure of the axioms for the Lebesgue integrals. Yes?
When you say subless space L2, do you mean L2 with one derivative, square integral with one derivative, square integral?
Yes, indeed.
So that would be,
okay, sorry.
No, I mean,
the
one point is that we know what you're talking about.
Yes! Thanks a lot. You know, I began by, I'm a computer scientist. So that's and so this one requires a Lebesgue integration, and to prove that it's a Hilbert space. So we began by trying to axiomatize, and then we were not very sure of the good axioms, on the good hypothesis, on the big theorems. And then we began to be unsure of what we were doing, and then we said, well, stop. Let's formalize it from scratch and get good theorems that are correct so that we can build upon it. And so we needed Lebesgue integration. And then we will need many other things because it will not be over there, but it justifies that we need indeed Lebesgue integration. So that's what I promised. I will talk about Lebesgue integration, so measurability, measures, simple functions and how to integrate them, and of course Lebesgue integral. I will stop to non-negative functions because it's all the proofs we've made for the moment, and it's already a large chunk. So measurability. There are many ways to define measurability, and given a set, so we have a basic set which is E and a subset of E, how can we know it's measurable? There are a bunch of different definitions, and we chose the one with the generator sets. So we have a set of sets, which is the generators here. So I said I was using this one, so that we have a set of generators, and then we said that the something omega is measurable either if it's in the generators, or if it's empty, or if it's complementary is measurable, or if it's a countable union of measurable sets. And so these are also called sigma-algebras. So you can use both. I usually use measurable because it's the way I think of it. And so it's an inductive definition, which corresponds to what you can find in the textbooks. Well, one definition in the textbooks. And so you can make induction. And I really used induction on these things. That was very, so it was very surprising for mathematicians, but we made induction, and that was very nice. And the theorems were easier to prove than what we expected. So it must have been a good definition. And we also defined the generators on R bar, because we need these generators to define the measurability. And so we have, among others, chosen, for example, on the real numbers, we have generators which are the closed intervals, and on the R bar, we have the half line from one point to the infinity. But we can have other generators, and we proved it that we can change generators, because you can have closed intervals, but you can also have open intervals or open semi-intervals and so on and so forth. You can even have them either on real numbers or on rationals. So it's, all of this is working, and you can switch to generators if you want. And you can even consider as generators the opens of the R bar, and we were able to prove that was a bit complicated, to prove that these generators are equivalent to the generators being the open, which are usually called Borel sigma-algebras, if I remember correctly. So this was proven, not easily, but that was, so that we can switch, well, any of the generators that the mathematician expects. And then we have measurable functions, which is kind of, this was straightforward because it's definitions that you can find in textbooks. So a function is measurable if this set A f of x is measurable for all measurable sets A. So you just write it like in mathematics. And we proved a bunch of lemmas, including the sums, scalars, and so on and so forth. So everything is all right. And one thing that we used a lot is to consider the restrictions on functions on a subset, because we usually have a function and we cut it in pieces and study with each species. And we have been trying a lot of things, and the most useful things was to use the characteristic functions, meaning the functions that is worth 1 when you're in the set and 0 when you're not in the set. And for instance, you have this theorem, which was very useful, meaning that if you have measurable functions and you consider another one which is equal on a subset A, then the characteristic functions times this function is measurable. So that you can, in fact, you have your function and you cut it in pieces, you proved it's measurable on each pieces, and you can fit everything together to prove it's measurable. So we used a lot of subsets and characteristic function for handling a bunch of things. Okay, now we have measurable, which is kind of easy because you take a set and you return a property. So it's either true or false. And then you have measures, and then you return a value. And we had difficulty, and we end up kind of axiomatizing what is a measure, meaning we say what a measure is supposed to satisfy. And so we have a bunch of properties. So the measure of empty is 0. A measure is always non-negative. And we have this sigma additivity, which said that if you have a bunch of omegas which are disjoint, then the measure of the union is the sum of the measures. So this is a kind of generic measure, we have an instantiation of that. We have the direct measure, which is not interesting. Nevertheless, it means that our formalization is not absurd. And so we were able to consider any measure and create some kind of Lebesgue integration with any measure. But we plan to do also the Lebesgue measure at one point. And for that, from this very generic measure, we are able to prove many of the textbooks properties for the measure, including this one, which I wrote both in Coq and in mathematics, except I did not write the hypothesis. Meaning that if you consider the measure of a finite union, then it's smaller than the sum of the measures. And that was kind of easy. So you can prove this with any measure, and the previous properties are both satisfiable by a real measure and useful enough to construct real theorems. And then simple functions, that was hard. So a simple function, well, for mathematicians, it's very easy. It's a function that takes only a finite number of values. Okay, so we have two examples of simple functions. So that take a finite amount of values. And mathematicians have a very funny way of defining them, which is written here. It's this formula. And it says that the function is equal to the sum of the characteristics. I think I forgot a y. Yeah, I forgot a y, sorry. And so they have this definition with the characteristic function, except that you have to sum over something which is finite because you're simple functions, but which is not always finite. And we tried various definitions for simple functions, something like 3 or 4, and we're always stuck. Because well, at least in Coq, I don't know in Lean, we like to sum over a finite set of values. Because summing of an infinite set is kind of problematic. And so we have tried various definitions, and I will show you what we succeeded in doing. So this is the most easy definition. So a function has a finite number of values if there is a list that lists all the values. Okay, so there is a list, L, such that all the values of f are in L. So that's okay. That's okay, that's nice, except that L is not unique. You may have several L. You may have useless values, you may have twice the same, you may have things like that. So it's good, but it's not unique. And we defined something which is a canonical finite values canonic, which is the same, except that we want L to be unique. And so for that, we require L to be sorted strictly, in strict order, and we need to have all the values taken, meaning there is no useless values, and of course all the values of the functions are in L. And this one is unique. And by the way, we are able to construct the second list for the first one and prove that it's unique and so on and so forth. And then we have this mathematical formula, which is if you want to integrate a simple function, you sum over all the values taken and you construct it like that. So you sum the A and the measure of the values where the A is taken. And what we've been doing is that we have some kind of property saying that it's a simple functions. So it's both, so it's linking a function and the list. And it says both that the list represents the value of this function, that the list is canonic, and we have also some measurability. So I will just not talk about it, but we have some hypotheses on the measurability of the subsets. And then simple functions are this thing, meaning that we have a strong existential on the list, so that we can get the list from the proof. This function is just, well, it's just this function, meaning that it's too long to fit on the slide, so I just did it. And then the integral of the simple function, you take the function, and you take the proof that it's a simple function. And then from the proof, you get the list, and then you sum over the list this function. And that worked out to be reasonably good, especially we proved that the value does not depend on the proof. Because if we have one simple function with two different proofs with a simple function, then we get the same integral, which is rather reassuring. And indeed. And so we were able to prove all we wanted. And so that's not very nice to look, and it requires a strong existential and so on, but it's doing what it's supposed to do, so we were happy. And we were able to prove all the theorems we needed about the sum, multiplication by scalar, change of variables, which was hard, and many other things. So everything that you expect.
So,
yes?
Can you explain again that thing about not depending on the proof? So the
This,
is indeed a proposition, or does it contain data?
Both. In fact, the integral of a simple function takes two inputs. The first input is a function, and the second input is a proof that this function is indeed a simple function, because this function only applies to simple functions. And so in this proof, you have both the list and some proof that the list fits with the function.
So the list is inside, it's not
yes.
the list.
The list is inside because it's here. So inside a value of type SF, you have both the list and the proof that the list fits the function. Yes, because I want to be able to extract the list. Because if it was in type, I would not be able to extract, because I need the list itself to sum over it. So that's why I need a strong existential and a set.
Because you want the thing to actually run.
Yes, well, not really, but I want to.
About it running, you could just define the list to be the image.
Yes, but then how can I be sure that it's finite? Yeah, we've been trying that, and then we just, just once again, and just so that we have been. I'm still not sure it's the perfect solution. I'm still, I would not bet that it's the best solution possible. I'm just claiming that it works. And that's more than I can say of many other solutions we tried. So that's, yeah. I'm kind of modest on these things. So that's, I would not bet, but at least it's working. And anyway, this should be hidden to the user, because the user will use only the integral of the function, not of the simple function. So it's kind of, it could be abstracted and it could be changed without the user seeing it. So that's why I'm not very embarrassed by that.
But all these encoding of simple functions, you look at what is done in Isabelle, because actually they have a simple function in Isabelle or, right?
They don't have the same logical framework, and so this was not directly applicable. So that's yeah, we have some problems that they don't. So yes, we looked, but that was not working like we wanted it to work.
What do you mean by the change of variable?
It means I have, how can I explain that? Yeah, it's, can I explain that, or can I show the code? I can show you the Coq statement afterwards, because I'm not sure I can explain without the support. So I'll answer it after that. Yes, or I'll be late. So simple functions can be integrated. And now I will integrate any function, because that was my goal, of course. And so this is a mathematical definition, which is, it's the supremum over the integral of the simple functions which are smaller than f. And this corresponds to this figure, meaning that I consider a simple function which is smaller than my curve, and I integrate it, and I take the supremum of all this. If you want another way to see it, Riemann integral, it splits vertically, and takes the value and sums. Logarithmic integral, it sums horizontally because it takes all the values possible and then it sums over the measure of the values that are taken. So instead of vertical, it's horizontal. It's another way to see it. And I like it to make the parallel between the both. And so, surprisingly, it was very easy to do in Coq, meaning that we write it like in mathematics. Well, it's longer, okay. So it's the least upper bound of a set, which is the set of x, such that there exists a simple function, which is smaller than the function that I'm trying to integrate, and that has the integral, which is x. So it's really looking like that. And so we were able to define this integral and, of course, prove theorems. And I will show you 3 theorems. First one is the Beppo Levi, which is also called monotone convergence, meaning if you have increasing functions that goes toward f, then you can exchange the integral and the limit. So it's an exchange theorem between the limit and the integral. It's for non-negative functions. And we have another one, which is called Fatou-Lebesgue, which is also an exchange of the infimum limit. I'm doing too much mathematics in French. The limit of the fn's and the integral. So you can, you have it's not an exchange because it's a smaller or equal, but you can link the two. And the last theorem I wanted to do, I want to focus on a theorem which was a hard one, and which is kind of complicated, which is the integral of the sum is the sum of the integrals. The one last thing, I've not formally proved it because it was really complicated, much more than the previous ones. And so the expression in Coq is very easy. It means I have 2 functions that I can integrate, and the sum of the integral of the sum is the sum of the integrals. Except that the proof was some kind of piece of cake, because it needed something called adapted sequences, which are simple functions, which are a sequence of simple functions that are going to this f by staying under. And so we were able to prove that if we have some adapted sequences, then the integral of the function is the limit of the integral of the simple functions. So that's the first thing. And then we had to define the adapted sequences. And what's very interesting is that this is the way adapted sequences are usually defined, meaning you take this function, f, and if the value of f is too big, then you return n, which is your kind of local supremum. And if not, you make this, this kind of rounding here. This is a floor of something which will be about f of x. And it will be, in fact, the rounding of f of x. And that can be written in Coq like that, because this value here is exactly a rounding to a fixed point format in computer arithmetic. Incredible. Computer arithmetic strikes back. And so I began by writing this expression and began to prove things, and then I saw that I've already done these proofs, I knew them, it's useless to do them again, and so I've switched the definition to use the rounding for the flock library that I've been developing with Guillaume Melchion for a while now, and then all the theorems that were 50 lines get 2 lines because the proofs were already done in the library, so that was really wonderful. I think it was because I was doing the proofs that I knew that. So all the proofs got very easy with adapted sequences, and all the requirements were very easily proved because this was a rounding, so we already had all the properties of monotony and increasing and everything that was needed. And then we were able to prove that the adapted sequence was that. And so to get back to this thing, so we could get the adapted sequences of f with the previous formula and for g, and we sum them, and we're able to prove that this sum of adapted sequences is indeed an adapted sequences for f plus g, and prove that the integral is okay. But that was really much harder than what we expected from this, well, at least for the statement of the theorem. Conclusion? For Lebesgue integration, so we had our mathematicians, and now the pen and paper proof is 184 pages long. Okay, it's more than just Lebesgue integration, but it begins to be really a huge thing with about 1,600 lemmas and definitions. And we have been trying to fill all the proofs, and we have not yet done all these 200 pages, but we still have about the same numbers of lemmas and definition and 11,000 lines of code. So just to give you an idea of the size.
Pages of what?
It's detailed pen and paper proof in LaTeX.
Oh, I see.
I can show you this.
You made the roadmap.
Yes, the mathematician made the roadmap, and we have begun to convince them to make some Coq. So we have also mathematicians doing Coq proofs. And so we have a very nice LaTeX PDF file with colors, definitions, and so on, and links. So we can have also a graph of dependency. And this paper is, well, not paper, this report is 184 pages long. And the difficult part was handling subspaces, which is, well, I think every time I make a Coq talk, I'm talking about subspaces and problems with subspaces. And we have mainly solved them with the characteristic function, which was useful in our case. And having simple functions that indeed work and that can compute the integral was also kind of, well, harder, because it's so easy in mathematics. And it was so difficult to have the good definition that it was very surprising. And perspectives, of course. We want to handle functions with varying sign, meaning not only positive, but also negative and positive and negative functions. And we have begun, but it's not over, so that's why I'm not presenting it. And it's very easy because it can be the sum of the positive part and negative part, and everything is okay. So it's just, the proof are just not finished, but there is no difficulty here. We want to define the Lebesgue measure itself. And that's more complicated because it's, well, it belongs to the 184 pages, but it requires non-trivial things. So we have not yet really dived into that. And we are talking with Cyril Cohen, among others, who is developing a map-camp analysis library so that we can, well, at least talk, and eventually I would like to take advantage of the automations. And we need to write the corresponding article because it's still work in progress, unfortunately. I hoped it will be finished before my talk, but it's not. So this is brand new things because the article is not yet written. And then when we are finished, we need to define our Sobolev space and prove it is a Hilbert. So there will be easy things, such that, well, it's a vector space. Wait, but to prove it is complete will be much more complicated, especially as L2 is a quotient space. So we anticipate some problems. Well, but it's gonna, well, it's our big project, so it doesn't need to be solved next year. And we need to define the finite element method algorithm that will rely on L2, but we need to define it to prove it. And hopefully, in a large amount of time, we'll want to prove a real implementation of the finite element method, meaning a real program running on real machines. And it will include floating point arithmetic. But this is not, this is a secret. And I have absolutely no idea of the floating point part of the finite element method, knowing if it will be complicated or easy. We are trying first mathematics, because it will probably help us. And we are still a long time to go before getting there. Thank you for your attention.
Do you have questions? Great.
Which real numbers did you use? You got it out?
Yes.
No.
I don't think, no. I was gonna say a lie. We use least upper bound because we need it, and we even classical. So that's
Inevitable.
Sorry?
You can't do analysis without being enough.
Well, let's discuss.
I don't want to be in the middle of this fight. I do not. No. We to answer more specifically to that, for the Milgram theorem, we have tried to be as constructive as possible by kind of extracting the decidability hypothesis we needed. And so we have a bunch of excluded middle hypotheses on some things. And after doing that, we decided that it was too much a pain because we had very large hypotheses, and that was not useful, in fact. But we needed to do it in order to know if it was practical or not. And so after doing that, we decided to switch to the dark side and the classical side of the force. But I know he doesn't agree. That's, you know, that's.
Any other questions? Did you look at how they did it in Lean? Oh, maybe you did it first.
No, I did not.
We just checked the definition of simple functions in MATLib in Lean, and the definition is the image is finite and the pre-image of anything is measurable. That's all. And then they define Lebesgue integration with this definition.
So I'm jealous.
But probably it's classical over the place.
Yeah, but it was not that easy to do here. But well, I'm not really ready to switch to Lean because I will need floating point numbers. You know, I'm very attached to floating point numbers, so I will have to.
You should bring them with you.
That's another possibility, but I'm here to be convinced, really. I've come here to see what Lean has to offer me.
Jeremy, you know, the one who did Lebesgue integration is he here?
Joe, you back here?
Where are you?
There he is, all the way back. So it was Joe following a sketch. I mean, Johannes started it, and it was Joe following the sketch of Johannes. But it's, yeah. So I mean, so one difference is that's right. So Lebesgue integration, a number of theorem proofers have it. So Paul certainly, and Johannes generalized the construction of Isabel to the Bottom. It's a slight generalization, but it's the advantage that you get integral of complex valued functions or RF valued.
Yes.
In Joe, as Johannes and Joe have worked on the Bottom integral. So you should take a look at it.
Yes, I will.
Thanks.
Thanks.